Hello, today I'd like to speak about some recent work I did in a paper with my collaborators, listed here, on using field-level inference, a technique that allows us to go beyond two-point statistics to directly infer the underlying dark matter distribution in voids and galaxy clusters. So large-scale structure is one of the most important probes we have of cosmology, but also indirectly of new fundamental physics more broadly. The first reason for this is that it can allow us to extract information on the universe's initial conditions. That allows us to put constraints on cosmological parameters, but also on things like the level of primordial non-Gaussianity in initial conditions, which can tell us about how the universe formed. Secondly, we can combine it with early universe information, such as from the CMB, from which we can in principle learn about the gravitational evolution over the last 13.7 billion years, which can allow us to constrain the laws of modified gravity. Generally speaking, however, using large-scale structure as opposed to the CMB is quite tricky because of the nonlinearities inherent in gravitational evolution, which complicates the analysis. There are, in particular, two types of structures that I want to focus on in this talk: galaxy clusters and voids. In principle, field-level inference can tell us about other such structures, such as filaments or sheets, but they won't be the focus of this talk. So voids are empty regions of space which form from initial underdensities in the universe's initial conditions. They're interesting because they remain linear on quite small scales compared to galaxy clusters, and they're already widely in use as a probe of cosmology for this reason. In particular, the average shapes of voids can be used to constrain cosmology using something called the Alcock-Wyczynski test. More broadly, however, we can use information from the void density profiles to constrain theories of modified gravity. Galaxy clusters, on the other hand, are much more nonlinear, but they're also somewhat better understood in general. We have good predictions for their abundance, for example, and it's a lot easier to define them than it is for voids. To actually constrain physics with either of these, we want to measure properties such as the abundance, mass, and radius of these structures, so that we can compare them to simulated predictions. This can run into issues because there are many ways of defining the boundaries of voids which can give different answers, although that can sometimes be an advantage depending on what you want to do, because it allows you to define voids in ways that can probe different aspects or scales in cosmology. For the case of clusters, on the other hand, there's a variety of different methods for measuring cluster masses, which are often in disagreement with each other, and I'll come back to this later in the talk. But for both of these, I hope you can see that there's a common thread. We only really observe things like galaxies, which we can see, whereas the underlying dark matter distribution, which actually defines these properties, such as mass and size of a void, is something that we can't directly observe. So in principle, we want to be able to get at that underlying dark matter distribution. This is where field-level inference comes in. This is a Bayesian technique in which the fundamental idea is to model some field, f, defined over all of space, which we wish to constrain, given some observed data which depends on our field via a model. In general, that model will have some parameters associated with it. In our case, the field we want is the initial dark matter density field, so the initial conditions for the universe. And the model we have is a gravity solver, which models the evolution of those initial conditions to our present-day density field, combined with a model for redshift space distortions and galaxy biasing, which takes density fields and turns them into a galaxy distribution. The basic idea then is that we can construct a likelihood for our observed data and turn that via Bayes' theorem into a posterior distribution. Now, in principle, this will be a massive parameter space to sample for this posterior, but advanced methods such as the Hamiltonian Markov chain Monte Carlo method can actually sample this quite efficiently, provided our model is sufficiently fast to evaluate. We can actually go one step further than this, however, to extract a posterior distribution on something that is a function of our underlying field. For example, if we want to know the mass of a given galaxy cluster or the radius of a given void. So in our case, we can do this via a technique which we call posterior resimulation. The idea being that we infer initial conditions, which can then be put into an n-body solver, which then gives us a final density field again, however, at a higher level of accuracy than our initial inference was. with these resimulated samples, we can then estimate properties such as the mass of a given cluster in each given sample. And then, because we have many of these samples, we can then estimate the posterior distribution of, say, the mass or radius or any other property we'd like that can be derived from the dark matter density field. Now, an example of where this technique can be really powerful is in modeling of voids with something called antihalos. So an antihalo is a model of a void first proposed by Ponson et al., in which you take the initial conditions for a simulation, swap the sign of the initial overdensity field so that overdensities and underdensities are swapped, and then resimulate those reversed initial conditions to give you a new simulation. Then if you look for halos, which here we mark in orange in this anti-universe simulation on the right, they actually correspond to voids in the original simulation. And the beauty of this approach is that you're essentially putting voids and clusters on equal footing, which we know they are in the initial conditions because there isn't exactly as many overdensities as underdensities. So this preserves this very clear connection between halos and initial conditions and voids in their initial conditions. The disadvantage, of course, is that this only works if you have the initial conditions to begin with. And obviously we don't, on the face of it, have those initial conditions for the actual universe. However, through this technique of field level inference, we can actually get a posterior distribution for this initial condition, and therefore get a posterior distribution by posterior resimulation of the actual halos and voids themselves using this antihalos approach. Of course, it's not required to use this antihalos definition. You can use any void definition you like to actually do this, but it's just works particularly well for this work. So the code we're actually going to use to do this field level inference is called BORG, which stands for Bayesian origin reconstruction from galaxies. BORG is a highly flexible tool which allows you to perform a field level inference on initial conditions from a galaxy catalogue. But there's also recent work by Posterior et al. Extending this to weak lensing data. The input is a catalogue of galaxies, currently at fixed cosmology, though in future that will change, and the output is an initial density field on a grid. Now, the accuracy of this method will, in practice, always depend on the accuracy of the actual underlying model you're using. So in the implementation we used for this work, there are three basic steps. A gravity solver, which takes us from high redshift to low redshift. We have a redshift space distortion model, which puts everything into redshift space because we observe everything like galaxies in redshift space. And then a model which takes us from the density field of dark matter to an actual distribution of galaxies. So at every stage we're going to be introducing parameters which we want to infer, but they can be inferred jointly with the density field. So we're going to talk about some very specific choices that we make here, but it's worth bearing in mind that this approach is flexible enough to be able to mix and match and change these around if you want to do a more accurate inference that might be required if you have a different science case. So here's an example of the BORG algorithm applied to the 2m++ galaxy catalogue, which consists of around 70,000 galaxies with spectroscopic redshifts. The red points you can see here are actually the galaxies of this catalogue, overlaid on a background which is an initial density field evolved with an n-body solver to redshift 0. So you can see how the overdensities trace the galaxies as we'd have expected. What's particularly neat actually is that we even get an inference for what's actually behind the galaxy, even though we don't see any galaxies there, because the large-scale information from the galaxies allows BORG to actually infer what things it can't directly see. However, we found during the course of this research that getting this inference right actually requires that you have a sufficiently accurate gravity solver, but also one that is not too accurate that it's too slow. This isn't trivial because you essentially have to balance the accuracy against speed. If you're too slow but really, really accurate, you can't sample a posterior with high enough efficiency. But on the other hand, if you're too fast and lower accuracy, you're going to potentially bias the density field. As an example here, we compare two different inferences performed with different gravity solvers. In green, we have a particle mesh model with 10 time steps, and in pink, we have a Kohler model with 20 time steps. With the grey region, we are showing the mass functions we expect for both halos and antihalo voids on the left and the right, respectively. And we're comparing those to what our inferences actually give us. So as you can see, there's a huge discrepancy depending on what model you actually picked. And this sort of illustrates that the 10-step particle mesh model is nowhere near accurate enough for our purposes. It's leading to a significant overestimate in the masses. Essentially, this happens because it underestimates the density field for a given initial condition, and BORG compensates for that by increasing the initial density field, so that when you resimulate it with a more accurate solver, you get an overestimate in the density of the mass of the cluster. So it's important for us to extensively tune this model to get it right. But of course, what we mean by right depends very much on the question we're asking. In our case, we want to know about the highest mass clusters, around 10 to the 15 solar masses. So on the left, you can see for several different models how the masses of two clusters, Coma and Shapley, in our initial conditions, will actually turn out when you vary the number of time steps and change the different model around you're using for the inference. And these are always done at the same initial conditions, by the way. What we find is the obvious result that fewer time steps leads to less accurate masses. But what we really want to identify is which of these methods for the lowest number of time steps can get us an accurate estimate of the masses, which is given by the gray bar, which is when we simulate these initial conditions with an n-body solver. And we find that quite consistently that a 20-step Kohler model works best for this. In particular, we also experimented with the actual spacing of the time steps. So if you space steps linearly in scale factor, it's actually better than spacing them logarithmically for this particular usage case. So proceeding with the 20-step Kohler model, we performed an inference of the universe's initial conditions. Here I'm showing the masses we obtained for 9 large clusters in a local supervolume, against other estimates of the masses for these clusters in the literature. For the most part, for example, we match the X-ray and Zerner-Zavzovich methods, shown in orange and green respectively. Not so much matching the dynamical methods, shown in blue, but these also tend to be something of an overestimate compared to the X-ray and SZ methods. So this is an encouraging sign. We do note, however, that there are some outliers, such as Perseus Pisces, which has substantially lower mass than we would have expected in this resimulation. That may indicate some underlying systematics in the dataset. Now, we can play the same game for voids that we do with clusters. However, it's a little trickier to get the actual combined catalogue for this, because the constraints for voids live in a slightly different space to those of clusters. When we resimulate each of our MCMC samples, we'll get n different catalogues of voids, one for each resimulated initial condition, and the task will be to somehow combine these into a single catalogue. To do this, we came up with a matching algorithm. We'll have a look at the different catalogues and try to identify the same void in each catalogue. So you can see here in these two plots an example comparing two different samples of the Markov chain, the catalogue of voids you get, and it's highlighted in the same colors, this matching algorithm, objects which it believes to be the same void. Now you can see that sometimes you get voids which don't appear at all in the catalogue. And this is just a reflection of the posterior noise that's involved in this process. Sometimes they will not appear in catalogues due to the different high K modes which are occurring. That's an inherent part of this process, so we want to actually quantify how reliable a given void is. Our basic procedure for doing this is as follows. We first use the signal-to-noise ratio to remove all voids from all catalogues which are below some cutoff threshold. After that, we go through our high signal-to-noise voids and find candidates in the other n-1 catalogues that could be the same void based on their radius and distance. If that process throws up any ambiguous matches, we exclude them. So if there's 2 possible voids that could be the candidate for a given void, we exclude it. And we only retain those voids which appear in a significant fraction of MCMC samples. How many samples exactly depends on the void radius. We determine this by comparing the same algorithm applied to independent random initial conditions in order to estimate the rate at which voids that could appear in the same place with the same size by coincidence. We then use that to pick a threshold that excludes the vast majority of random matches of a given size, allowing us to give a pure catalogue of voids, which we are confident are not due to spurious random alignments. So importantly, this catalogue is not meant to be complete. It's meant specifically to identify the most well-constrained objects in the catalogue. So we're not going to find all the voids in a local supervolume. So we see this here for an example of a particular set of matching parameters that recovers most of the voids within 135 megaparsecs of the Milky Way, except for some of the lower mass ones, which will tend to be less well constrained. But you can see that when we extend this out to 300 megaparsecs, the low signal to noise further out means that we actually don't recover anywhere near as many voids at that distance. So this is telling us that for the most part, up to around 135 megaparsecs, our data is quite good and very constraining, but less so further out, at least for voids which we are very confident exist. In any case, once we've found these voids, we can then in principle then use them to constrain cosmology by comparing to the expected density profile that they should have. So you can see an example here in the grey curve is a lambda-CDM prediction of the density profile of voids, of these particular type of voids, antihalos. And overlaid on top of this, we've put a red curve which shows the density profile we found for our constrained voids using the field level inference. And we see that these, for the most part, agree with each other, up to some fluctuations which are actually due to cosmic variance. Now, this at first glance would seem to suggest that the voids we see in the local supervolume are mostly consistent with lambda CDM. In principle, therefore, we can use this to put constraints on modified gravity and on, say, massive neutrinos. So, in future, we hope to be able to make use of this with much larger data sets in order to expand the volume over which we can infer the density field of the universe. So this might only really be possible by using large photometric data sets, which will be produced through LSST, which of course will have lower precision redshifts compared to the spectroscopic redshifts we're using in this work. And that might make it trickier to identify galaxy clusters, which are much smaller, but voids being larger may actually be easier to do. That's something that's currently under investigation. But the possibility of using other traces and also actually sampling the cosmology is also something that's being heavily worked upon in BORG at the moment. All right, so thank you for listening to my talk, and I look forward to any questions you have.